Okay, so at last, everyone, good morning. We're back in the class. Let's have a quick review on the problem that we are working on from the last time. Okay, this is the example number 2. Okay, we have worked on beam number 1 and number 2 already. These two beams are the beams that we can call the secondary beam or the filler beam. Okay, they generally take the load from the floor directly, and you can calculate the uniform load acting on these two beams by using the tributary width multiply with the load per area. So that's exactly what we did last time. So with B1, you now have this tributary width of 1.6 meters. Brown. Okay, that's your tributary width coming from this width, all right, from the last time. And your total load is 900 coming from the information given to you here. Now, ladies and gentlemen, please also remember that in the future, if you work as an engineer, it is your job to determine these loads by yourself. Okay, and it is one of the most, if not the most important step in your work. It can be called something like design criteria. Okay, the load is your criteria. It is something that the performance of your structure has to meet. Okay, we will have the measurement of your understanding of the design criteria in the design class in the future. So the senior would know, because in the project of the steel design, you would have to be able to give us the criteria that you use on your project. That is the load that your structure will have to support. Okay, so with that, you now can calculate the uniform load acting on B1 right here, the load from that, bringing down here, multiplied by the tributary width, and then plus the weight of the beam itself. So you have the final number 1740. We can use that to calculate the beam. Now you need to pick the right length of the beam as well. And from the plan, you see that B1 is 8 meters long. You can use that to calculate. I think I have the number for you because I found the solution for this problem. So this will be equal to 6960 kilogram force, and this maximum moment will be equal to 13920 kilogram meter. Okay, you should know that if you have the uniform load case, this is the shape of your shear force diagram. Oh damn, what is this? Must be my daughter's doing. Okay, that is the shape of your shear force diagram. I'm not going to go through the details about this anymore, because you should have had this very clearly from mechanics of materials. You have the constant load, so it produces the linear shear. Okay, and when your shear is linear, it becomes the second degree curve for your bending moment. So your bending moment diagram is going to be like this. This area is positive because you have the positive area from the shear, and then this area will be, will be coming down because you have the negative area from your shear. But this is the basic stuff that is already covered in mechanics of materials. So I'm not going to go through that in details. If any of you have problem following this, you need to spend some time, make a review by yourself on the materials from the old days. Okay. So now we are up to the B2. The B2 is essentially the same as B1, as you can see, except the loading is different and the span length is different. From here, the tributary width that you can see is this one, which is 1.2 meters. The load is essentially the same. So right here for B2, it's 900 multiplied by 1.2 as the tributary width. So the W is 1380. Now we can calculate the shear. The shear is, yeah, we have that 3864, and the maximum bending moment shall be from this equal to roughly 54110 kilogram meter. So now we can focus ourselves on B3. Now let's coming back here and take a look at B3. Now I got a very good question from the last active session. Say, how do we figure out the system? You know, I could not finish the entire plan in the last time, so I didn't get to talk about the entire system. So from that question, I got a very good, it got me thinking, and I realized that I never mentioned it this way in the class. So I'm going to say it for the first time in the class, that generally, if it's a typical beam, except the cantilever beam, you guys should have 2 supports for each beam, right? You cannot have 1 support for a beam unless it is a fixed support. So you need to have at least 2 supports. So in other words, it's your job to provide 2 supports for each beam. So let's say if you look at beam B2 now, say this is your B2, okay? What are the 2 supports for your B2? The 2 supports for B2 would have to come from this point and then that point, right? Those 2 points will be the supports of your B2. So what are those 2 supports come from? It has to come from B3, because these 2 supports are on B3, and you have a series of B2. This is also B2 that needs 2 support here and here. And this is another B2 that needs support here and here. And when you look at the B2s now, every B2 has supports. And you look further, what would give the supports for B2? Because from the plan, apparently we don't have any columns to support B2. So when you don't have columns, you need to have beams. So B3 would have to act as support for B2. Okay, any question? And now when you look at B3, what would be the 2 supports for B3? Now you can see that we have columns here and here. So which means B3 will be directly supported by the columns. So after you calculate the B3, you would be successfully sending the load from the floor through the beam to the column. Okay, and once the load reaches the column, it is now ready to go downward to our foundation. What we are looking at now is the plan in the horizontal plane. Our job for the gravity load system is to transfer the load on this horizontal plane down to the foundation. So I can switch back to the lecture to show you this picture. You can recall that we now have this is our horizontal plane, right? B2 would carry this plane and send the load to B3. This is your B2. Carry the plane and send the load to B3, because B3 has to provide the supports for B2. And then in turn, B3 here will send the load to the columns. So when the load reaches the column, it is ready to go down to the foundation. So our job for transferring the gravity load on the horizontal plane is done. Okay, is there any question? So now let's have a technical aspect of the calculation of B3 a little bit. I think some, if not many of you, should be comfortable enough to take care of the calculation of this B3. Some of you, I hope just a handful of you, may struggle. Now, this is not a bad thing because it's not like the end of the world. I have to say that. You guys need more practice to handle this. But if you don't practice, you know, the small problem will become a big problem. But what you should know now from your mechanics of materials days, that when you see the beam, you should see the shear force and bending moment diagram right away, at least how they should look like. You know, in this case, you have the point load and you have the uniform load. And you should also realize that this beam is symmetric, right? So when you have a symmetric situation, you should know that, you know, one way or the other, the result on the left should look similar to the result on the right, correct? And this is going to be your center line of symmetry, okay? You know you would have the reaction. So the reaction here would produce the upward shear like this. And then because of the uniform load, this shear force diagram should gradually come down as a result of the uniform load, correct?
Yeah.
Yeah. Brown must be my daughter, really. Okay. So this, because of the uniform load, you must have the gradually declining shear force diagram. And you run into the point load or the concentrated load. Now, what the point load does to you is that it causes your shear force diagram to change abruptly, so suddenly. So your shear force will have to come down like that. And then let me try to use the dramatic color. Like this would do maybe. This is the result of point load, right? And then things would go on because you now have the uniform load that would gradually reduce your shear force. And then another abrupt change because of this point load. Okay. This is caused by uniform load. And now because of the symmetry, you know that your maximum moment is going to be in the middle, right? Knowing that much, you should also know that to have the maximum moment at the middle, your shear here must be 0. So no matter what you do, this is what your shear force diagram should look like. Do you agree or not?
Yes.
Right. Nobody's gonna kill you if you answer incorrectly. But if you don't answer, at least deep down inside your mind, you must know whether or not you know this already. This is what you must know from your days of statics and mechanics of materials. I did not know this, so I got a bad grade out of mechanics of materials. So I gotta try harder the next time. And you should know, if you practice hard enough, this kind of knowledge will stick with you for as long as you work as an engineer. Because let's say if you graduate and work as a millionaire, for example, is that a word? Anyway, you would not use this knowledge as a millionaire, so you probably forget. Okay, but if you work as an engineer, you should never forget about this thing, not even in your dreams. Okay, so now let's try to move on and see how our bending moment diagram should look like. Now, because of the slope at the shear force diagram, it's a linear. So this will force your bending moment diagram to be the curve, right? Because of the mathematical relationship, because you integrate the shear force diagram to obtain the bending moment diagram, correct? So it has to be a curve. Because of the sudden change of the slope, so this curve would not be as smooth as B1 and B2. So this is what you're going to get. Okay. So now, even without a calculation, you should be able to figure out how your diagrams would look like according to the load that you have on the beam. Because the load is some kind of function which would lead to the shape of the shear force diagram, and the shape of the shear force diagram would lead to the shape of the bending moment diagram. Okay, so now let's do some little calculation music to get the numbers. Now, because of the symmetry, you should know that you can easily calculate the shear here. I mean the reaction, sorry. The reaction should be, because you have 4 point loads, right? So and it is symmetric, so it's natural to assume that the support, each support will take 2 of them. Can I do that? Do you agree? Or if you wish to take the moment away, feel free to do that. It's the same. Plus the effect of the point, the uniform load. And if you look at the uniform load alone, let's say, I'm running out of this. Let's say do this. You have a beam, this beam. Can I write this beam as this? The beam with point loads, 4 point loads placed equally, and the beam with the uniform load. Can I analyze this beam like this? Yes or no?
Yes.
Yes.
Yes, of course. Absolutely. So it would make my life easier, at least in terms of the calculation of the reaction, right? This, ladies and gentlemen, is what we call superposition. If the situation permits, you can always break your situation into the small ones, analyze each one by one, and then add them up. Or to use the more engineering term, superposition them. So I can easily calculate the reactions by using the superposition. That is, I'm going to calculate the reaction caused by the point load coming in from this case, and then I'm going to calculate the reaction caused by the uniform load. Coming in from this case, the beam is 6 meters long, right? So that means the reaction due to the uniform load would be 3 meters multiplied by 300. Right? You guys following me? You can always, if you plan ahead, if you can see the big picture, what you're doing, it's like a piece of cake. So Vmax, the exact number is 3628. Okay, so that's the number that we will begin our shear force diagram. And the tributary width of the B2, that's 1.2 meters, right? So that means this is 1.2. So can you calculate this next number quickly? Or did I ask you to calculate that? Oh yeah, shear force and bending moment diagram. This point is I'm sorry, it's 86236.
the reaction is to be 8.
Yeah, 88628. Right. I'm sorry. It's just my mind doesn't work properly. Sorry. Yeah. Thank you. Thanks a lot. I saw 8, but I said 3.
Okay.
It's inexplicable, really. So don't let that happen to you in the exam. Okay. So the unit here is kilogram force. Okay. So it's 8628, and then this location. This number would come down by the amount of 1.2 multiplied by 300, right? So this is 8628 minus 1.2 multiplied by 300, because that's the distance, right? 1.2 meters, and the uniform load is 300. So there you have it. It comes down to be kind of confusing. It's 8268. 8268. So forgive me for not writing the unit. I'm running out of space. And at this point, because you have faced the sudden change caused by the point load, so it's basically this number 8268 minus 3864. Yeah, so thank you. So that is 4404. Thank you. 4404. And then this number is just going to be 4404 minus 1.2 multiplied by 200 again. And this is 4044. How's that? 4044. And then at this point, it's just 4044 minus 3864. And that is 180. So you should now pray that 180 minus 0.6 multiplied by 300, but not 200, 300 should give you 0. Okay, so that's the end of the shear force diagram. And you should not really take long to calculate this at all. If it takes long for you to finish this one beam, it is okay for now. But you must understand that engineers should marvel at this. Okay? It is like the easiest thing in the world for engineers to just calculate these numbers. Okay? So now let's move on to bending moment diagram. Now the first value of the bending moment diagram should come from this area of the shear force diagram, right? This area should give you this number, right? And maybe because if you look at the problem, I am only asking for the maximum. I'm not asking for anything. I'm just asking for the bending moment diagram. So it would be nice if you could provide this number, but if you could just provide the maximum moment, that'll be okay as well. But let's say you can do that, and you should realize by now that the area of the trapezoidal is the thickness multiplied by the average height, right? If you don't know that already, let me, you know that, right, guys? Let's say if you have the trapezoidal like this, the formula is the average, because you say you can cut this triangle and place it here. So you have the typical rectangle. So that's why we use the average height of the two sides and then multiply by the thickness. Okay, so for me, that's a very easy way to handle the trapezoidal. Okay. So with that said, you should be able to calculate this pink area, and the number is I can't read my handwriting. 10135, whatever. Sorry if okay, I don't know if that's correct, but it should be close enough. And then the next spot, my daughter is pretty good at drawing. She uses a lot of colors. Okay, I use this one. The next point here. Okay, one moment. The next point here would be the result of the previous number 10135 plus that area, plus the green area. All right. So it should be equal to 15206. And then the maximum moment would be the result of, again, let me try to use a similar color, okay? This maximum moment is 206 plus the orange triangle, which is equal to 15260. Okay, so that's how we can use the area of the shear force diagram to calculate the moment. But let's say I only want the maximum moment. Do I need to go through all this? The answer is no. I can easily use the free body diagram to obtain my maximum moment, right? Which means I can easily cut the free body diagram of the beam, not straight enough, at the half. Okay, now I know my reaction is 8628. I cut the free body diagram at the half. That's where the shear is 0, isn't it? And then I have the internal moment coming in here. I know it's M max because it's at mid span. And then I have 2 point loads. And then I have the uniform load. I can just take the moment here. Sigma moment equal to 0. You know, I understand that some of you it takes a while to take the moment, but you know, you're in the 3rd year. When you take the moment, you don't just come in and, okay, this is clockwise, this is counterclockwise, dream about it for 5 minutes. And then you begin your, you know, writing down your equation. You're in the 3rd year now. So this should be in your blood. You should see that if this is your fulcrum, your reaction would give you a clockwise moment, right? It goes this way. And the rest, the uniform load, the point load will give you the counterclockwise moment. You should be that quick already. Or if not, you should try to be that quick. So the maximum moment can also be calculated by using the free body diagram. It's going to be 8628 multiplied by the distance to the midspan, that is 3 meters, minus the moment due to the point load, which is 3864. But now you have 2 point load, so I can just use one number multiplied by 2 lengths, right? So the length from the midspan to the first one is 0.6, and then plus 1.2 more, so that's 1.8, and then minus the moment due to the uniform load, which is 300 multiplied by 3 square over 2. Yeah, too quick for you, Junior? Hello? You get the same number. No matter what approach you use, you should get the same answer. and that is 15206 kilogram meter. I know what I've just done can be a little bit too much or overwhelming for some of you. If you don't know which numbers come from, how did they come from, you should ask now. Hello? Any question? All quiet. You know, you can talk to your friends now in the class. I don't mind. I never turn off anyone's microphone. I know you guys miss that in the classroom. You can talk to your friends. So you may use your electronic device to chat with your friend now, or or you can just ask me. Please don't let your doubts go by. Don't be afraid to ask a question that your friends may think, why don't you know this? It doesn't matter what anyone thinks. What matters is your understanding. Okay? Any question? No, no car. Crystal clear, right? Crystal clear. Yes.
Yes.
Yes. Okay. So I think the time is pretty much right for us to have a break, even though we lost 15 minutes to the discussion on the class, but that's okay. I think we should be able to catch up. So let me stop the record.